I thank everyone come to this very nice workshop. Thank Hiro to give us such opportunity. And also thank you again for showing up so early. And but luckily now we reached the point. Yeah. And the title of my talk is the spin-Hall effect in topological semi-metal. I think today you already, all this week, we already learned what is topological insulator, topological semi-metal, and what is spin-Hall, and how it is used for a device. And here I just simply combine these two together and show you some simple results. And let's start from the simple observation we know about this mode scattering. And this picture tells us science. Suppose we have an atom here, nuclear here. If an electron come here, when it passes by this atom, it has this high velocity together with the electric field from the nuclear. Effectively, it feels a magnetic field. And this is exactly the mechanism of spin-optic coupling. And this magnetic field will let the electron favor a special spin direction. Then the downspin preferred to turn this way, the upspin turn that way. And this mechanism is well known. And like, for example, is already applied in the as a spin detector for photon emission. And then this in general happen like supposing a material. Now we know a 2D material, for example, we pass through the current. Then the spin up and down electron will just travel to opposite direction, turn to left and right. And usually, in some case, if it's a non-magnetic material, then this turning, they are equivalent. This up and down current, they are equivalent. But if, suppose we break the up and down symmetry a little by making it magnetic, by magnetic field or some magnetic impurity. And here we break the equivalence. Then we get a net current in this direction, right? In the transverse direction. Then in this case, this net current is, you already know, is called the anomalous Hall effect here. And however, even here, they are totally cancel each other, these two currents. And we still get actually a spin current because up and down travel to opposite direction equivalently. This means there is a transverse spin current. Then this is called anomalous Hall effect. This is spin Hall effect. And all in short, like here, what is spin Hall effect? It is in a material we apply just an electric field, it will generate a transverse spin current. And here from this picture, somehow people thinking for years this kind of effect is just simply from scattering, like impurity, then take it as an extrinsic effect. And well, this is true, happens in many material. And then until 2003 and 2004, at that time, this is Hiro's generation.
Dinosaurs.
And then people realize, well, it's not necessary only from the impurity, and actually for many material, only from the band structure, there's an intrinsic effect can generate such spin Hall effect. And then this is closely related with the barrier curvature from the band structure. And here, when electron travel in the material, it will feel a fixture's magnetic field. Then different spin just start to turn. And this is a pure effect from the band structure. Therefore, it's called the intrinsic spin Hall effect. And at that time, people already start to think, well, here we know the first early proposal is on the doped gallium arsenide. And at that time, people already start to think whether there are some spin Hall insulator, not only metal, but there's an insulator, but the band structure still give you a magnetic field. And from that, from the spin Hall, people start later soon get the quantum spin Hall insulator. And this is already known. Then from the 2D quantum spin Hall, then get the 3D. Later, this is called a topological insulator, get the new name. And then we get this topological insulator, study about these surface states. People realize even there are some topological metal, semi-metal, they have similar surface states. And now we reach the new Fermi by January this year. And well, this is the idea going and going. And then.
Are we going to call them the Bernoulli experiment? I think we should.
Oh yeah.
Sure, no problem.
And yeah, let's just I just repeat a little more like what is the YSM metal. We as know in the bulk band structure, the valence and connection band they touch at some special point, and this point becomes the singularity point of the barrier character. Actually it's the like a monopole of that magnetic field. On the surface we have the Fermi arc, and related with this 3D Dirac coil and this Fermi arc, there are a lot of exotic quantum phenomena was predicted. For example, the Kerr anomaly and this kind of quantum orbital. And well, in short, the bulk band is a kind of 3D graphene band structure. On the surface, there are Fermi arc-like surface states. It is similar to topological insulator, but also different because it's arc. And then let's see the material. We already learned. Yeah, like first is this tantalum arsenide family of materials, and they have a complicated band structure. And later comes the new type, the type 2 YSM metal. But in principle, what we can roughly learn from band structure is first, the bulk is a semi-metal. Actually, close to the Fermi energy, there are not only wire points. Actually, there are a lot of bulk bands, trivial bulk bands. This is the Fermi surface. Like from the transport experiment and the calculation, except the wire point, these small points, there are also large trivial bulk carriers. And this is the same for this type 2. By definition, for sure, there are a lot of trivial bulk bands in this electron and hole pockets. Then it's natural we see in experiment this material will be very metallic because of this bulk bands there, and at the same time this is a special dispersion and topological protection like from from the barrier curvature, as Lucas said, and give us the high mobility and a very high magnetic resistance as observed in tantalum ditelluride and niobium phosphide, all these materials. And yeah, this is a type 2, the photo emission is the same. This is surface states, but with the surface states, we also see there are trivial surface states. At the same time, they are mixed with the bulk bands. And since we talk about this is a topological semi-metal, well, usually we assume the band structure is as simple as this one. However, this is a reality. Reality always gives you such complicated one. Here we already assume there's no defects and no other things, and it's already very problematic. And since here, I just would see like these topological states. What can we do here? Just a little, like some discussion about the possibility. How can we use these states? Since we argue this, especially the topological surface states, they live on the surface, metallic, and they are protected by the bulk. They are very robust in this sense. And since they are on the surface, whether they can affect or do something for the surface-related process, like electron travel on the surface, or even more like a kind of ambitious proposal, like whether they can work for catalysis, like in chemical reaction, this catalysis, whether it can happen. And one thing really encouraged us is first, here, as Benjamin already showed, that in the gold surface, we already found the known Rashba states, they are indeed topological states. And gold, platinum, these metals, they worked as catalysts for years or for centuries. And then whether these topological states play some role or do something there is still an open question. And then here also on the surface, these topological states, because of protection, they will be very robust there. They will, if they help to the chemical reaction, they will give a very robust support for that. And this is, okay. This is just a kind of proof of principle. What in Dresden we did is like we put this YSM metal material and tantalum arsenide them and into water to mirror the water splitting. It catalyzes the water splitting. In principle, it happens like it absorbs, the solar light is absorbed by some molecular absorb the light. Well, metal doesn't absorb the light here. And then this excited energy is electron is transferred to the catalyst. And hope a chemical reaction happen here, water gets splitted, then we get hydrogen out. And this is mirrored hydrogen generation split, the speed. And well, it's not that perfect, and but at least it might work for this. And well, now so far we are still struggling with how to improve this catalyst reaction. And this is just one part. I want to just quickly finish it. This is the main. Let's think about whether the spin Hall effect in the YSM metals. As we said many times, YSM metal here, this singularity point, the monopole point, there's huge barrier curvature. At the same time, there's strong spin of the coupling. These two together naturally tell us there might be a strong spin Hall effect in this related material. And then here from the yesterday from the talks of Hong Xiong and Chiming, we already learned about if we have a good material, have a large spin Hall effect, it can be used for the spintronic device. And then what I try to let's just close the loop. Let's use this new Fermi or semi-metal, especially semi-metal, and back to the intrinsic spin Hall effect. And yeah, just this is just calculate the number, whether and how much they can contribute. Well, for sure, this depends on material. And then this is a really toy model from the quantum spin Hall effect. And let's understand a little what kind of band structure can contribute a spin Hall effect. And we know the first quantum spin Hall model tells us about a mercury telluride. The main band structure is there's a band inversion here. Two conducting band and valence band overlap. After that, they open a gap, and by small the coupling. And as long as this gap opening, with Fermi energy actually in the gap, we get a quantized spin Hall effect. And here, this when project band structure here, this is the spin Hall conductivity distribution. You see, this spin Hall conductivity is mainly contributed by the band inverted region when they cross and open a gap, when in this range region. And when we tune the Fermi energy in the gap, we put in the gap, we get a quantized spin Hall conductivity. That's why it's called quantum spin Hall. And then when we shift the Fermi energy away from the gap, then you see the spin Hall conductivity just quickly go to 0. This means if we want to get a large spin Hall conductivity, we need some band cross there. Band cross, and then we open the gap. And if you put the Fermi energy inside of the gap, you might get the largest value. Well, this is the model. Actually, it's only this quantized value here only happen for 2D material. If it's 3D, there's a KZ dispersion. Then this is not necessary to be quantized anymore. However, it's a similar principle. Like we need a lot of band crossing, and we need smaller coupling. And suppose smaller coupling is just negligible, but there's band crossing, then we have some problem. Like here, if your Fermi energy not cross exactly the band touching point, and you lose it, you really get 0. And in a real material, there's no way you can guarantee the material will do that. And then let's have a look at the tantalum arsenide band structure. This is the first paper by Bernwig and colleagues. And you see this is simple band structure. The complex about main information is here. You see, without smaller coupling, we see there's a lot of band crossing. And smaller coupling simply open the band, open the gap. Then the Fermi energy will not exactly inside the gap, somewhere still cross the bands, but roughly inside the gap. That means this material, there are a lot of band crossing. Oh, actually, these band crossing points in the K-space, actually they form a ring, they form a nodal ring. Like along this ring everywhere, band gap is 0 without similar coupling. Similar coupling simply gap this ring out. Then at some low symmetry points, we get the wild points. And then here, this material from band structure, we already see like here, there are a lot of band crossing. And here, at the same time, it's sure there are a lot of bulk carriers because these bulk bands still cross the Fermi energy. And then also here, this complex band structure, or this a lot of band crossing, actually is a kind of positive message for us. And then this is simply our numerical calculation about based on the barrier curvature. And what we did is we simply we start with this band structure information, the band, ab initio band structure, and the wave function. Then we get the back curvature. We calculate the spin Hall connectivity directly, and this the nodal ring you remember, and then we get the spin Hall connectivity. This is the distribution. I just made a projection to some YZ plane. You see clearly is that this strong color, this blue color, and this strong red color, right? This large color, they all distributed around this nodal ring, original nodal ring, exactly because of the band inversion. Then, when we integrate out them in all the K-space, we get the total spin Hall connectivity. We get some value like 800 for tantalum arsenide. Actually, I will mention that here, this sigma xyz, what does it mean? Here, sigma xyz simply means we apply electric field along y direction, then that will generate x direction spin current. And this z means the semi-polarization of this spin current is along z direction. Because this is a tetragonal material, it's not necessary to be isotropic. And actually, indeed, if we pass the electric field along different direction, we will get very different spin current. And well, here, this value for reference, like platinum, the well-known spin Hall material, its value actually is around 2000. And however, I think yesterday we learned for a material to characterize its spin Hall property, is one important property is the spin Hall angle, not only spin Hall connectivity. It's the spin conductivity over this charge current conductivity. And since we know here, PT is a real metal, and now in some sense we are still working with the semi-metal, then we believe this material is charge conductivity will much lower than platinum, but how lower? So far we are not very clear because usually this value, the device was built for thin film. So far for this material, the thin film are still not ready. And well, since we have several materials, they are just an example about these 4 materials in this family. And they show you, they have some difference. Well, for example, this table. For example, sure, tantalum arsenide shows the strongest value. And it's obvious tantalum arsenide has the strongest spin orbit coupling here. And well, here, this is the energy dependence. Since the Fermi energy, where the Fermi energy is, whether it's in the band crossing gap or crossing some other bands, it really matter. And here you see some peak value. We have this give us a direction, like in what kind of direction to dope the material to manipulate it. We may get optimize the spin Hall effect. Since in the band structure we know there are wire points, they are somewhere near the Fermi energy. However, these peaks they are not necessary means these peaks are the wire points. But in some sense, we can also from a toy model we can also understand a little more. Actually, this point means something. And here, this is just a toy model, not a material. And here we know, like, first the material, we know these 2 monopole give us the Berry flux give us a chain number here in this region. If you only, this is a K direction, along this KZ direction. Here in between, we get a non-zero chain number actually is 1. This, we get a anomalous Hall effect. This anomalous Hall conductivity, well, here, there's only 1 spin channel here. Then we can get this is spin Hall at the same time is anomalous Hall at the same time is a spin Hall because it's fully spin polarized. Also in the energy range, if we tune the Fermi energy cross the wire point, actually we also get a very large spin Hall connectivity. This is the intrinsic contribution. Interesting is here. Let's assume we put the Fermi energy here. Actually, your bulk Fermi surface just a point. We don't have Fermi surface. Here, this is but there are still a non-zero error contribution. This is purely tell us this is an intrinsic effect from the band structure. And then, yeah, here we already know in topological insulator there are already several very interesting results to use it to build a spin Hall device. And this is what I learned from yesterday. And there. Currently, the problem is the bulk of topological insulator is too conductive, and this make the spin Hall very weak. However, if make the bulk very insulating, this becomes another problem. You don't want the spin-hole material to insulate. Otherwise, the current will go from somewhere else. And thus naturally, this semi-metal just avoid this problem by itself. By definition, the bulk is kind of conductive, and the chemical potential somehow is, I would say they are kind of pinned. Let's see. Suppose we have some inverted band structure, and this is a case of Ti. Ti, the Fermi energy doesn't like stay here, but it's go here or either here. But if we, at the same time, we have some metallic wire points, then naturally it's very easy just to put the Fermi energy here, because these carriers help just guarantee the Fermi energy lie most closely to this inverted region. And good, in the very end, I would thank my postdoc students. They did most of the work. And I especially thank my collaborators, Claudia, at least for she paid the bill. Yeah. And thank Haim and Yulin. And also thank a lot of discussion with Leslie and Andre. And also my student questions for Hiro. Okay, I thank again for everyone attended this workshop. And here, this is my most favorite cartoon. This tells us like, well, these two peaks, mountains, represent, well, two wire points. You know, this is a Fermi arc. What I try to say is just like this workshop, we have many different mountains. They are singularity point of the knowledge in different expertise. And then, yeah, I think in this kind of peaks, as long as there's something happen, it will be topological. Good, thank you very much.